everyone, and welcome to this explainer. We interact with highly complex systems every single second of our lives. From the exact moment we check our phones in the morning to the specific routes we take to get to work. But have you ever stopped to wonder how all of those overlapping, dizzying systems avoid completely collapsing into total chaos? Well, today, we are uncovering the invisible math that's organizing our world. We're looking at the hidden architecture sitting right beneath the surface of modern technology, keeping everything running smoothly and efficiently. We're talking about graph theory, and more specifically, the absolute structural limit of networks, the crossing number of graphs. Okay, let's dive into this. How exactly do we untangle the modern world? I want you to just imagine the sheer scale and density of the networks connecting our everyday lives right now. Think about the billions of overlapping signals beaming from cell towers, the millions of intersecting flight paths up in the sky, or, the endless labyrinth of roads in any major metropolis. If you drew it all out, it's a massive, impenetrable knot of connections. Engineers, city planners, and computer scientists literally have to take these massive, highly dense networks and untangle them structurally. If they don't, data and traffic can't flow, and the entire system crashes. So, to understand how we actually untangle these massive webs of data, we rely on foundational mathematics. Dr. Raphael Tumbelkon from Sam Rotolongi University outlines the baseline definition we need here. A graph consists quite simply of vertices, which are basically just points or nodes, and the edges, which are the lines connecting those vertices. Now, while these basic components are mathematically straightforward, they quickly scale up into massive, often totally intractable networks. But by reducing a sprawling, complex system down to its basic structural skeleton of vertices and edges, we gain a framework. We finally get a way to mathematically analyze the invisible, scaling forces that connect our world. Now, these abstract structures map out highly complex, real-world relationships of staggering density. Take a social media platform, for instance. It's built on billions of concurrent nodes and edges, creating a massive web of interactions. Transportation systems rely on these huge graphs, where sprawling cities are the nodes and complex highway arteries are the edges. In the internet itself, it relies on a densely packed graph of computers and servers worldwide. Graph theory is exactly what allows computer scientists to manage this unbelievable scale. But computationally, managing and visualizing this much interconnected data introduces a monumental structural challenge. And this brilliantly illustrates our main problem: visual and systematic chaos. Because if you throw nodes randomly into a space and connect them based on relationships, you guarantee an incredibly high density of edge crossings. And in graph theory, these intersections are a severe problem. A highly tangled graph destroys visual legibility, making a structural math completely unreadable to a human eye. But even more importantly, it destroys algorithmic efficiency. Whether it's a data packet trying to find the absolute fastest routing protocol through a server farm or an automated transit system managing rail lines, excessive edge crossings turn a highly functional network into a messy, inefficient labyrinth. So, untangling this mess requires some intense mathematical optimization. This is really about moving from mess to success. A disorganized, messy graph makes data visualization wildly ineffective and dramatically slows down routing protocols. Conversely, an optimized, clean graph is structurally organized, algorithmically easier to analyze, and inherently sound, and that drastically improves overall system performance. So minimizing edge crossings is absolutely not just about making a diagram look aesthetically pleasing. No, it is a rigorous optimization problem designed to reduce deep structural complexity and improve the functional reality of the system itself. Which brings us to our mathematical hero, the crossing number. The crossing number of a graph is the absolute minimum number of edge crossings possible when that graph is drawn on a flat surface. It acts inherent structural complexity. It falls strictly into one of two categories. First, we have planar graphs. A planar graph is defined simply as a graph with a crossing number of exactly 0. This means it can be flawlessly mapped on a flat surface with absolutely no intersections whatsoever. A non-planar graph, however, inherently has a crossing number greater than 0. Because these networks are simply too densely connected, even with the absolute most perfect algorithmic optimization in the world, they will always contain mathematically unavoidable crossings. Now, what's really interesting about this slide is how these mathematical limits have intense real-world engineering applications. City planners must heavily optimize public transit maps, driving the crossing number as low as theoretically possible to prevent routing confusion for passengers. In computer hardware, specifically printed circuit board or PCB design, the stakes are even higher. Every single unavoidable crossing in a non-planar circuit requires engineers to add a new physical layer or a via to route the signal over or under another. That directly adds manufacturing cost and introduces potential points of failure. And in communication networks, actively reducing these structural crossings allows data to travel with vastly greater efficiency. So, the crucial point is exactly what Rafal Tumbakan highlights here. Crossing numbers are not only theoretical concepts in mathematics, but also practical concepts used in modern technology and engineering. The drive to find that mathematical floor and arrange data pathways more efficiently is the very foundation of network architecture. Advanced mathematics like this isn't isolated to an academic blackboard somewhere. The continuous, intense effort to minimize the crossing number is directly responsible for the speed, safety, and reliability of the infrastructure powering our entire modern society. So, I'll leave you with this. What invisible math is organizing the device you're using to watch this explainer right now? Deep inside your hardware, physical pathways were heavily optimized by engineers fighting tooth and nail to reach the absolute minimum crossing number. And the global network, whether it's a data packet trying to find the absolute fastest routing protocol through a server farm or an automated transit system managing rail lines, excessive edge crossings turn a highly functional network into a messy, inefficient labyrinth. So, untangling this mess requires some intense mathematical optimization. This is really about moving from mess to success. A disorganized, messy graph makes data visualization wildly ineffective and dramatically slows down routing protocols. Conversely, an optimized, clean graph is structurally organized, algorithmically easier to analyze, and inherently sound, and that drastically improves overall system performance. So minimizing edge crossings is absolutely not just about making a diagram look aesthetically pleasing. No, it is a rigorous optimization problem designed to reduce deep structural complexity and improve the functional reality of the system itself. Which brings us to our mathematical hero, the crossing number. The crossing number of a graph is the absolute minimum number of edge crossings possible when that graph is drawn on a flat surface. It acts as a mathematical floor. It dictates the inherent structural limit of any network. Look, no matter how advanced your routing algorithm is or how cleverly you arrange the system architecture, the crossing number reveals exactly how many intersections simply cannot be avoided. It is a strict, undeniable lower bound for your network's complexity. Let's move to and see how this builds when we try to actively untangle a graph. Reaching that minimum crossing number is a mathematically intensive optimization problem. The process involves placing the vertices, routing the edges to establish the relationships, and then computationally rearranging the vertex positions to iteratively reduce those intersections. And trust me, this isn't just a manual puzzle. Finding the exact crossing number is often an NP-hard algorithmic challenge. Computer systems literally have to constantly iterate through spatial arrangements, constantly shifting the architecture to approach that theoretical lower bound. And they only stop when that hard mathematical limit of unavoidable intersections is finally reached. So based on a network's I really want to leave you with a provocative question to ponder today. What kind of graph are you currently standing in? Think about your morning commute. Are you traversing a weighted, directed graph? Look at your own friend group. Is it a fully connected, undirected graph? Start looking at the world around you through the lens of vertices and edges. It kind of changes how you see everything. In future explainers, we're going to dive way deeper into the amazing tools used to traverse these networks, like breadth-first search and minimum spanning trees. But for now, just remember the incredible invisible math connecting your world. Keep learning, keep mapping out your connections, and we will see you in the next explainer.